Hello and welcome back. My name is Fatima Garba Yusuf and this is Electronics. So in the previous video we talked about the definition of corrosion, the nature of corrosion, the factors that affect it, and so on and so forth. We also talked about the types of corrosion, where we explained briefly about the different types, such as the crevice corrosion, the stress corrosion cracking, the oxidation corrosion, pitting corrosion, uniform corrosion, and so on and so forth. Now, apart from all this, there's also the hydrogen grooving, which is a common type of corrosion that is found in pipes. And it is formed due to the interaction of a corrosive agent that is possibly flowing through the pipes and then corroded pipe constituents as well as hydrogen gas bubbles. And these bubbles usually remove the protective coating once they come in contact with the material. I also showed some pictures depicting different types of corrosion, such as pitting corrosion that forms a deep pit, the crevice corrosion that occurs in a localized area or a localized portion, as well as the grain boundary corrosion, which is mostly common in alloys that occurs at the grain boundary. And there's also the stress cracking corrosion that is usually due to the application of a tensile load or tensile stress. Next, we are going to talk briefly about corrosion prevention and some of the common ways that corrosion can be prevented is through galvanization, which is a chemical process, as well as electroplating. Just like in electrochemistry, where you have a cathode and an anode, but in this case, we build on the principle of electrochemistry to prevent one of the metals from getting corroded. Next is painting, which is by maybe the commonest form of prevention for corrosion. Even those that didn't go to school know that if their metallic bench or metallic desk gets corroded, they paint over it, then for a significant time it won't corrode again. There's also greasing, also application of grease, then regular cleaning, because of course presence of impurities also contributes towards the facilitation of corrosion. Then there are some other activities such as the use of corrosion inhibitors and also anti-corrosion protectants, or even drying agents, because moisture often leads to the facilitation of corrosion. Another one is also passivation. It's also another type of method that can be used to prevent corrosion. Now next we are going to discuss briefly about some of the formulas that are used to solve problems associated with corrosion. We might not be solving problems in this video, but we will be talking about the formula and the values that we need when we are trying to solve problems on corrosion. So the first one we are going to look at is corrosion penetration rate, or CPR. And here the formula goes R equal to KW divided by rho AT as the denominator, where K is actually a constant and it can take either of two values depending on the unit of A, which is area that is used. W is the weight loss of the metal in milligram for a time T. And of course the A is the surface area of exposed metal, that is the area that undergoes the corrosion. Even if you have a metal tube and not all of it is exposed to the atmosphere, then when you are calculating your surface area, you're not going to use all the 6 sides and edges and so on and so forth. And it is typically measured either in inch square or centimeter square. Then there's the density of metal, which is usually used in gram per centimeter cube. Then next we have the corrosion rates. The corrosion rates can be calculated using the formula small letter I divided by NF, and the small letter I is a letter that represents the current density. So as you can see, we have two formulas here. You can either calculate your corrosion rates using I divided by NF or W divided by TAM, where T of course is time, A is area, and M is the molecular weight. So here we are defining the variables for R equal to I over NF, and we said I is the current density, and the current density is calculated by seeing capital letter I divided by E, and the capital letter I is the corrosion current. So N is the number of electrons. For example, if you have iron 2, then your number of electrons will be 2, while your Faraday's constant is a constant, 96,500. The next formula we're going to look at is weight loss. Of course, we're not talking about weight loss for humans. We're talking about the loss of weight due to corrosion and degradation of a metal. Maybe because it has developed holes or something like that. And it is typically calculated by using these previous formulas for R. When you just make W the subject of the formula and you equate I over NF to W over TAM. So when you make your W as the subject of the formula, you get your W to be ITM divided by NF. And if you replace your capital letter I with small letter I multiplied by A, you have A multiplied by small letter I TM divided by NF. So here your time is in seconds, your current is in amperes, your farad F is your Faraday's constant, 96,500. Your M is your atomic mass. Your N is your number of electrons either produced or consumed, depending on the metal, whether it's producing electrons or receiving them. And then A is the area encountering corrosion. As earlier explained, we are not going to calculate the total surface area all the time, except if all the areas are actually exposed to the environment that is causing the corrosion. For now, we are going to look at the last formula, which is on the kinetics of oxidation. Remember that, of course, corrosion is actually related to oxidation. And for you to understand corrosion very well, you need to revisit your kinetics of oxidation. What happens when oxidation happens? What happens at the anode? What happens at the cathode? And so on and so forth. But then there are a number of equations that were developed that are said to portray or you can use to calculate your weight loss. There are three. It's either your oxidation follows the linear law, which is W over equal to KT. It's either your oxidation follows the linear law, where you have just one constant K, that's W equal to KT. Sometimes you can see this K as K subscript L to show that it's the linear law that it follows. Or it might follow the parabolic law, which calculates W square and says it's equal to KT plus C. Here we have two constants. We have K and C, while T is our time. And also K in this scenario can be written as K subscript P to differentiate it from the other K. While for the last one we have the logarithmic law, and it's depicted by K log open bracket CT plus A is supposed to give you W. So here we have W equal to all this. And of course, the definition of terms, your T is time, your W is weight loss, while K, C, and A are constants. If it's the linear law, you just have one constant K. If it's the parabolic law, you have K and C. And if it's the logarithmic law, you have K, C, and A. Now, the application of this is that sometimes you might be asked to determine whether a particular scenario of corrosion follows the linear law or the parabolic law and the logarithmic law. Even without being told, you can see that the linear law is the easiest to determine. So if you are given maybe a table that contains time and your weight loss, perhaps for 2, 3 samples or 2-3 runs, then you can calculate your K for the first run, calculate your K for the second run, and you compare. If they are the same, it simply means that they are following the linear law. As for the parabolic law, you need to solve simultaneously, and it's of course wiser for you to test whether it's the linear law first, since it's the easiest one. So when you calculate and you determine that it's the linear law, then good and fine, you don't even need to test for the other ones. But if it's not, you move to the parabolic law, and then you move to the logarithmic law. And of course, if it's not the linear law and it's not the parabolic law, it has to be the logarithmic law. So in subsequent videos, we are going to solve examples based on some of these equations, and you can practice more on your own, check out textbooks, and so on and so forth. So see you in the next video. Thank you.